Hey YouTube, gonna do another review and teardown of a component for that big battery bank, and I will slowly make my way towards completing that project. I have a Giandel 600W Pure Sine Inverter, some quick specs on the side there, total harmonic distortion less than 3%. I wish I had my oscilloscope working so I could actually verify that. So, cardboard box. Seems pretty sturdily packed. We have some accessories on the side. Some more accessories. Some little rubber mounting grommets for vibration, I guess vibration resistance. That's a nice touch. And the inverter itself. Styrofoam pack, and here we go. We got an inverter here, and it seems to weigh a good amount of weight. It's 1.73 kilos. Alright, let's get back to this. Accessories first, we have a twin lead to low duty alligator clip. It's kind of light duty, but I guess for testing purposes I wouldn't really trust this on anything real. Have a set of alligator clips for connecting it to battery posts. Seems to be like a good, decent rubber, and I can't tell what gauge wire this is, but it appears to be at least like an 8 gauge. It's bigger than 10 gauge for sure. I think it's an 8 gauge, but it looks like it's a silicone rubber or an EPDM rubber. So it's, you know, it smells too much for a, well, actually no, I think that is silicone. So it's actually pretty good quality cables that you get to start with. And this thing, which is going to be a remote switch, power and fault. Let's start with opening this up to see how it's built. Even though that's not why you're here, you want to see the inverter. We're going to look at everything. Plastic self-tapping screws and an RJ11 jack, I think is what they are. It's been so long since I've ever had to deal with a landline telephone that I can't even remember what they're called. Yeah. Got a QC Pest sticker on something that literally has like 2 LEDs and a button. Yeah, this is as simple and straightforward as you could get. Little PCB, 2 LEDs, not even 2 resistors. The resistors are somewhere else. Yeah, a button and 2 LEDs, that's it. I don't know why I was expecting more, but you know, is what it is. Also, it helps if I put this on the correct way so you can actually plug the cable in. Comes with mounting screws, which is nice. Remote power for the remote on-off for the inverter would be nice if you're actually installing this like in an RV or something. In my case, I think what I will end up doing is building a custom version of this and just holding on to this if I ever move this inverter to a different project. Instruction manual, warranty card, and a couple other bits, and then we'll get to the real inverter. They have, they're saying use M4 screws on these shockproof pads. Got some miscellaneous literature, thank you card. Really don't care about that, and a user manual. So let's see what the listed specs are. I think this is an Australian company, so they have several different models. You've got an output voltage of 110 to 120 or 220 to 240. I guess it's not configurable. 50 or 60 hertz, but I guess these are switched around. 12 or 24 volt input. Surge power to 1200 watts. It's got a USB output. it does have a USB output. That's kind of neat. No load current. Quiescent currents at 8.8 amps. 800 milliamps is quite a bit of quiescent current for an inverter. I guess they tried to get that as low as possible, but it still seems like it's a lot. Overvolt protection at 16 volts plus or minus 5, so yeah, it's an inverter. Not much more to say there. Let's put this away and get on to the next step. Alright, inverter. How do we get in? Oh, those cheeky buggers. They have tri-wing screws. I need to find a special bit for that. That is a surprise. I think this is the first time I'm ever going to need my triangle screwdriver bit. And does it fit? It does. It does indeed. Cheeky buggers. I guess before I get too far into that, let's take a look at the outside. We got fuse holder, not fuse holder, fuse covers. Let's see if these are actually holders or just covers. Can I just unplug this directly? Or do I actually have to unscrew that? Oh, these are just covers. I shouldn't actually unscrew that. Yeah, okay, that's a little misleading. I guess I should tighten the screw back up. So it's got a 30 amp fuse, I guess another 30 amp fuse. Are these in series or parallel? It looks like they're in neither. Maybe? We will open it up and find out. Put those off to the side. So I guess on this side we've got our AC outputs. We've got our soft power button. It's not a hard power button that actually physically disconnects the power. It's just a soft power button that turns off or wakes up the inverter. So it would be interesting actually. Let's measure what the quiescent current is when the inverter is off. Because if it's drawing something like 0.8 amps when it's off, that would be very disappointing to see. Actually, let's power that up. Set that there, and small spark. 0 amp draw when fully off. Turn it on. Oh, undervolt. Oh no, it's running. Yep, power. It's back down to 0 amp draw. Yeah, 0.3 amp. 0.3 amp quiescent current. So it's actually a good deal lower than the manual says. It's only drawing 0.3 amps at 12.9 volts. So maybe it's thinking it's the worst case scenario at its lower end. I'm at 10.3 and we're up to almost 0.4 amps, 10 volts at 3.39 amps. Still, it's not bad at all for a quiescent current. So let's turn that off and keep going. Also, in retrospect, I powered this thing up now, which means any capacitors inside are going to be charged, and I'm going to want to maybe be a little more careful when going into this. Yeah, what could possibly go wrong? It's just 110 volts AC. Okay, we've got interesting. So it looks like, before I go any further, I just want to see if there's any voltage DC on this. Three millivolts. Yeah, okay. That's so it looks like you've just got ground to this binding post to the case, and AC neutral and AC line split across these two outlets. The USB port, the soft control, all seems to be localized here. So I guess some of these resistors are really just to set the, I guess, the charge mode for the USB port. Yeah, it's pretty well designed, and this board is actually very well mounted. You've got these two screw terminal, I'm just trying to think of the correct name for the component. You've got almost like screw terminals. Let's bring this camera down closer and refocus it. It's almost like screw terminals that are soldered into the board. So when you plug a USB cable in here, this board really is not going to flex at all. It's very sturdily mounted. So that's good to see. Let's jump around to the other side here. And we pull that up a little and refocus. Good enough. I'm actually impressed that they use triangle screws, if only for the sake of providing a product that can't be easily tampered with, but since when has that ever stopped? Also, let's just take a second to appreciate these fasteners. They actually have some knurling on them that helps prevent them from backing out. So if they're torqued to the correct amount, I guess based on the design specs, you don't need a lock washer, which means one less part for an assembly line worker to forget when they're assembling this unit. Alright, here's the input side. Let's just measure the input voltage and bleed off any power on that, if there is any. There's still 9 volts on there. Yeah, let's just do that. Small spark, nothing too big. 300 millivolts in building. Alright, so it looks like they are in parallel. This looks like it's solid brass as well, which is good to see. It's not some kind of cheaped out combination of. You've got two 12 gauge wires. You've got this big brass bar here that goes to the two fuses, and they're parallel together. And then you've got the negative terminal. And you've also got a fan here, which looks like it's pretty decent. It is a 12 volt 0.1 amp fan. Alright, so let's see how we can get into here. It looks like one of these panels just slides out without any hassle. This is very serviceable. This is incredible. I thought this would be like a piece of Chinesium, but, you know, I stand corrected. Simple stamp steel? Big steel? Yep, definitely steel, magnetic. Alright, so what do we have in here? Very little excess wiring, which is going to be good for, I guess, airflow, thermals. Yeah, so this would be mounted like that, and that would be mounted like that. We have a whole bunch of things to look at, so let's bring this camera in a little closer and maybe refocus it. I think that's sharper. Cool. So we've got some capacitors, got more capacitors, we've got switching transistors on both sides. We have what looks to be a, oh, that's interesting. What's that? QC15, QC3, QC number 8. A couple stickers on here as well. A buzzer. What looks to be some opto isolators and some voltage isolation slots, a voltage adjust, which I guess allows you to trim the output voltage. Another card type device here, two card type devices. What's that? Almost like it's just a stray wire. Okay. You've got the main transformer for your switch mode. So you're going to have transistors probably parallel here. They're either going to be MOSFETs doing PWM, or they're going to be transistors or IGBTs. They're probably MOSFETs. I don't want to disassemble it that far. I'm not desperate to get a look at the bottom side of this PCB. However, you're probably paralleling these into pairs of two, so you can get an H bridge. The H bridge runs the primary side on this transformer. You've got these diodes here, which is interesting. They're on heat sinks. So I'm kind of wondering why the diodes are on the heat sink here. You've got high voltage capacitors here. Unless... Interesting. Okay, I might be wrong. It could be that these four transistors are running the voltage step-up operation, and it looks like there's a little thermistor or something, a temperature sensing element, on a rubber pad that's pushed up against this, and they've got Kapton tape all over the place. They've got Kapton tape to make sure that the sill pad is aligned correctly. There's an electrically insulating but thermally conductive silicone pad, and these metal bars that hold the MOSFETs in place. So it's not actually, this is a really good build. You've got this bar here with two M5 screws. This is a steel bar. It's magnetic, lightly magnetic. So I think what is happening is these four MOSFETs are running an H bridge, which drives the primary on this transformer, which then feeds through these two pairs of diodes that are heat sinked. You've got this interesting heat sink configuration. Maybe I can get a better peek from this angle. Yeah, let's go to the other camera. Let's maybe focus it out a little bit further. Yeah, so you've got these two pairs of diodes. They're pretty beefy diodes, and they're on these little heatsink tabs. So that's a great way to heatsink them without adding extra heatsink mass. As long as you can calculate the power dissipation based on the forward voltage, you can probably determine just how much airflow and how much thermal mass or dissipating capacity you need. So anyways, it looks like it takes the input voltage, runs it through an H bridge here, through the primary side, it steps it up, rectifies it into these two capacitors, and from the looks of it, they are not in parallel. This is interesting. Yeah, I think that these two are actually seriesed. So there's like a minus 170 and a plus 170 volt. In case you didn't know, actually 120 volt AC is actually like 170 volts peak to peak. Sorry, not peak to peak, but from ground to peak, so you need plus and minus 170 here. So I think it generates the high voltage here, which then goes through these MOSFETs with PWM to then go through this inductor and this capacitor. So this is an LC network. Basically, this section here is the high voltage side, which is a Class D amplifier effectively, and it takes your plus and minus 170 volts DC, runs it through the H-bridge, through the inductor, through the capacitor, and then straight to the outputs. Which also makes sense because you've got your high voltage isolation here, so this must be the low voltage side. You've got a couple analog components on this side, which appear to be op amps. There's a lot of analog glue here, a lot of capacitors and resistors. So I think this is just an op amp card that facilitates. Let's see here if I can get a better look. I've got an ST chip there, but I really can't make it out, and I don't want to poke too far in. And what's interesting also is that they've actually got a series of resistors here to bleed down the output capacitor, and a series of resistors, I guess, for safety. And it looks like this little module, or this little board, is responsible for the 5-volt quick charge output on this inverter. It is a little disappointing to see that it's just free floating like the other inverter card and controller cards. It looks like this card's the one that actually has the microcontroller on it, because you've got a crystal and what looks to be a PIC microcontroller in here, and a couple other components in there. It's a little hard to see. Let's get a flashlight in there. We've got an IR, 2 IR parts, and alright, so I think this top board actually has the MOSFET drivers for both sides. Possibly. It's a little disappointing to see that this isn't fully connectorized, that I can't just remove it, but I guess it's also an economy thing. It looks pretty well designed. I'm not sure what this paper-like substance is, and there's another paper-like substance, a sticker here. On the transformer, I wouldn't be too worried about it, because this is all potted and sealed. But on the output side here, you've got 120 volt AC and this residue that if it were to arc over and carbonize, it's just going to form a resistive track. So a little disappointing to see that there's some adhesive tape residue on here. I don't know if it was just used during processing to hold down components, but they left behind some nasty. So just clean at least some of it off, and hopefully that'll be good enough. Seems to be very well built. I don't really have any more critiques on it, and I don't want to disassemble it further in case I can't get the MOSFETs to align or something. But let's appreciate another touch that was done. The board itself isn't secured. It's in 2 little slots, so it could slide forward and backwards in this aluminum extrusion. However, they seem to have put in these molded rubber tracks, basically. So the entire board is actually shock mounted. The entire board floats inside this track. There's this rubber gasket in here, which provides some vibration isolation, because guess what? You're going to have an inverter. It's going to be mounted to a car. Oh yeah, turn off that multimeter. So that's a very nice touch, that even though they provide these little silicone, I guess, vibration damping stoppers, grommets, for the mounting holes, or the mounting tabs, they go a further step, and they actually vibration isolate the whole board, other than the MOSFET. So the case is still mechanically coupled to the MOSFETs, and the vibration will get into the board there, but the majority of the board is still vibration isolated to some degree. It's dampened. Plus it means the entire board is also electrically floating from the case. So I guess that's also a good touch in case there's some issue on the circuit board itself. This is a very well designed inverter. For 600 watts, it is pretty bulky, but ultimately you get what you pay for. I mean, you don't get a small compact 600-watt inverter that's pure sine wave, and it seems like it's pretty well built. The electrical methodology is pretty sound. You know, they've got all the little touches. Even on the high current traces, they've got stitching on the vias to join the top and bottom traces together. Oh, you can't really see it on camera here, but yeah, you've got stitching on the vias here, 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 and here for the high current side, which makes sense because you've got yeah, it looks like plus V goes directly to the primary on the transformer, minus goes to this big ground plane here. So I'm guessing that the MOSFETs underneath, there's the other trace that goes to the primary on the transformer. So the DC, the low voltage DC side of it is really just confined to this corner of the board, and then high voltage AC, or high voltage DC to AC conversion dominates the upper half of the board. I guess the only other thing is maybe this isn't for the quick charge, but this is just a general module to provide logic voltage on the board. But it looks like the trace goes to here, and it's not a small trace either, so this could just be USB charging. I think that's about it. I'm 30 minutes into this teardown video about the Giandel 600-watt Pure Sine Inverter for North America. Seems to be very well built and very well designed, so, you know, thumbs up on Australian design there. Pretty sure it's Australian anyways. Australian design, Chinese built. Close enough. Anyways, if you like the video, thumbs up, leave a comment, let me know what kind of videos you want to see, and by the time this video comes out, hopefully I should have a pattern built up where I can do a video every week on a Wednesday and release it, so look forward to more regular content. Yeah, that's about it. Peace out.